Hi, my name is Sophia Greisner, and I'm going to be walking you through a problem in Chapter 16, Acids and Bases. We are going to be solving and comparing the pHs of a weak acid and a strong acid when the molar values are given. So, let's start working through this. Well, I'm going to start with strong acid because that's going to be the easier calculation. So, you can take a breath and we'll start easy. All right, so our strong acids are any one of the big six. So here I've listed our big six strong acids. You can use them mnemonic, so I brought no clean clothes. That's going to help you memorize it. I underlined the parts that correspond with it, and they line up with above. So you can use this mnemonic to help you memorize it. But if you can't memorize them all, it's good to go into the exam knowing at least one strong acid and being pretty confident in it. I always go in knowing HCl. That's my go-to. So choose a go-to. So we're going to use HCl for this equation. So we know acids donate their hydrogen. So it's going to donate it to the water and create a hydronium ion, which is how we're going to measure the pH, by the concentration of hydronium ions in the products. Our next step, how do we find this concentration? Well, with a strong acid, it's easy. And we can see a strong acid is indicated by this one-directional arrow. The strong acid completely dissociates in water. So the concentration of the initial HCl, which is 0.0275 molar, is going to be the same as the concentration of the hydronium ions. So let's just write this out so you can visualize what I'm saying. So here it is. So we have the final concentration, which is great because we are also, to solve for pH, we use the equation pH equals the negative log of hydronium ion concentration. Super simple math. We're just going to plug this into our calculator. So you're going to type negative log, put in your concentration, and that's going to pop out a pH for you. In terms of sig figs, why did I choose 4 sig figs or 3 decimal places after the, 3 decimal places after the decimal? Well, when we log something, we're going to do 3 decimal places after the decimal point. So that's why I have 1.561. And that's our answer for our strong acid. See, not too bad. Okay, so it's going to get a little dicier when we start getting into weak acids. Not too much harder, so don't worry. But first we're going to choose our weak acid. Well, what are the weak acids? Well, it's any acid that's not a strong acid. And if you're still coming up with a blank, go to the chart. That's going to be given to you in the exam. And here's what it's going to look like. And we're going to need a Ka value, which we know this because in the question, it says you cannot use the x is small assumption. And we are going to use that in a quadratic. And in a quadratic, we're going to need a Ka value. So here's our charts of Ka values in weak acids. So we're just going to choose one of those. I'm just going to choose HF because it's the first one there. Any one is going to work for you and you can get a correct answer. But we're going to go HF for this problem. Again, same thing, write our equation. The acid is donating. Acids donate. So, and it's creating the hydronium ion. Now we're going to calculate the Rice table because we can't assume the final concentration is the same as the initial because it's a weak acid. So we're going to set up a Rice table. So first, our reaction. We already did that. Great. First step done. Next is going to be our initial concentrations, which we know is 0.0275 molar for HF, but we don't know the final. So we're going to assume that little to none ionization has occurred and the initial concentration is 0 for the products. Next, we're going to do our change. So reactions are going to be negative, the coefficient x. Since there's no coefficients in this problem, it's just going to be negative x in the reactants and positive x in the products. Next, we're going to have our equation. So this is where you're just going to take your initial minus or plus the change value you have. So that's what we're setting it up as. Okay, now this is where our Ka value comes in. So here's our Ka value. And we're going to set up our equation. So we are going to have our products over our reactants. So our products are the x's, but I already put together. So that's our x squared. So the x's are multiplied over the HF concentration. And we're going to set that equal to Ka. Well, now we want to get the x squared on one side. So we're going to multiply across. So 7.10 times 10 to the negative 4th is going to be multiplied by 0.0275 and by negative x. And that's what this is going to look like when we do that setup. Well, now we want to use the quadratic. So we're going to have to get them all to one side. And when we organize it, here's them all to one side. Set equal to 0. Now, we're going to want to use the quadratic. I listed my A, B, and C values. You will be given the quadratic on the exam, so I wouldn't worry too much about memorizing it, but definitely get comfortable with it. So this is all the values plugged in, and I use plus because the other, when we use negative, we get a value that's not possible for a concentration. So we're going to use positive when we're doing this. That gives our x. Our x value is equal to our concentration. So we have that's our x value, that's our hydrogen concentration. Now the same thing, log of pH equals negative log hydrogen concentration. Plug that in, we get a pH of 2.355. Now the problem's asking for the difference though. So let's solve for that. We're going to take our two values, subtract them together, we get a difference of 0.794. So we can say HCl's pH is 0.94 greater than HF. And that's the problem. Good job, guys.